So this is my last lecture. So if you already get bored by my lectures, don't worry. This is the last one. Okay. So I will talk about our understanding for the pairing mechanism in twisted Bilayer graphene. So one of the basic idea is that we think that this twisted Bilayer thing is very similar to a heavy fermion system. Okay, this paper is posted a few months ago. Okay, I think previous talks have given some introduction to this system, so I think I don't need to spend a lot of time on the model. So basically we have so in the low energy model for twisted Bilayer graphene, we have two valleys, and we can treat this valley degree of freedom as a inner degree of freedom, like a spin, right? So we can label all the electronic states by at least two indices. One is the valley. It equals to either positive K or negative K, and the other is the spin. And so in 2011, it's predicted that there should exist a magic angle where flat bands emerges. And in 2018, this sample is realized in experiment, and many interesting phenomena were observed. I think the most striking one are the coexistence of superconductivity and the correlated insulators. So if we look at the phase diagram here, one may recognize that it's very similar to that of the cuprates. So I think that's why it attracts so much attentions. And before the details of my talk, I would like to briefly summarize some facts about the superconductor phase in this system. So first, this experiment reviews nematicity in the pairing order. So I think it shows that the critical current or the critical field has an angle dependence, and it has a C2 symmetry. So the original system has a C6 symmetry, but now it shows that the pairing phase, the superconductor phase, seems only to have a C2 symmetry. So it seems there is a nematicity. And as also discussed in the last talk, half an hour ago, the gap shape measured in STM shows a V shape, and one can compare the size of this gap to the superconductor critical temperature, and it turns out that the gap is much larger than the critical temperature. So this reveals a BEC-like pairing. So you have a stronger pairing than the superconductivity. And actually, this fact also aligns with the previous experiment where the coherence length is measured, and the measured coherence length turns out to be comparable with the Maury lattice constant. So that also means that the pairing is quite local in real space. So I think these two experiments match each other in picture. And also, it's important that the superconductor coexists with strong with the correlated insulators. And there are some experiments shows that when the Coulomb interaction is further screened, it seems that the TC might be enhanced a little bit. So this might suggest a phono-based mechanism. Yeah. So this is, I think these are the key features has been observed in experiments, and in the following, I will try to convince you that I'm not sure I'm able to, but I will try to convince you that these features could be understood using a unified picture. Okay, so let's think what's the possible pairing mechanism. So as the phase diagram looks very similar to that of the cuprates, one may expect a cuprate-like mechanism. But I think it's quite different because here no magnetism is observed around the superconductivity. So I think it's quite different. And one may also expect a BCS pairing, but the BCS pairing also is also in contradictory to many facts, like BCS pairing cannot have a nematicity, it cannot exhibit a V-shaped gap, and it cannot explain the BEC-like feature. And when we talk about the electron phonon mechanism, one may need to consider the retardation effect. And we also quantitatively calculated this effect. It turns out that the column repulsion is too strong for this mechanism to take place. So in summary, we find that neither BEC or cuprate-like mechanism could explain the superconductivity in this system. So after we did a lot of calculations, and in the end, we found that the mechanism in twisted Bilayer might be very similar to that in fluorides. So let me talk a little bit about the fluoride. So it consists, it's formed by a superlattice of these cages. Each cage has 60 carbon atoms. And between them, there are some cations. And the effective model for this superlattice is a Hubbard-like model with 3 orbitals, T2U. I don't remember the representation, but it's a 3-orbital Hubbard model. And the sum energy scales in this system is similar to that in twisted Bilayer. For example, it's strongly correlated. The column repulsion U is larger than the kinetic energy. So in twisted Bilayer, in twisted Bilayer graphene, the column repulsion is also stronger than the bandwidth. And the second, as each cage is made of many atoms, so there are strong electron phonon couplings within each cage. But the induced attractive interaction is quite small. In this system, the induced attraction is merely 0.1 eV, so it's 1/10 of the repulsion interaction. So naively, one would not expect a pairing in this system because the column repulsion will dominate. So we do not expect superconducting, but it turns out this system is superconducting, and the TC is actually high. It's I don't remember the number, but it's higher than most BCS superconductor. And actually, the pairing mechanism for this material is has already been well understood in 20.0. So the mechanism behind this is that is like condo physics. So when we consider a single cage, we can regard the invariants around this cage as a bus. And if we treat the invariant as a bus, then at a proper energy scale, condo physics will take place. That means some local quasi-particles will be formed around this cage. And it turns out that the renormalized interaction, in the renormalized interaction, the effective U will be strongly suppressed, but this attractive interaction is less suppressed. So that's how this G wins over this U. So I think this system is quite similar to twisted Bilayer in the sense that in twisted Bilayer, a unit cell is like a Mori site, and it consists of hundreds of carbon atoms. So it looks like so it's very similar to a cage. A cage is also formed by many carbon atoms. And second, in a Mori unit cell, there are many atom vibration modes, phonon modes that couple to the electrons, and they may give rise to a attractive interaction like J. So but in fluorides, the pairing symmetry is S wave. So but we found that in twisted Bilayer, the analog could give a P wave like a D wave like pairing and explain the nodal phase. Okay, so that's a motivation. After we do all the calculations, we find that some others already pointed this out a few years ago. For example, in 2018, Wilson and his collaborators write in their paper, and they say that the pairing mechanism in twisted Bilayer might be similar to that in fluorides. And also in another paper by this Fabricio in 2019, he names the electron-photon coupling in twisted Bilayer as a valley Young-Taylor effect. I think that name also suggests a similar mechanism as the pairing in fluorides, because the electron-photon coupling in fluorides is also called Young-Taylor effect. Okay, so before I explain the superconductivity, let me explain our model, our model for the electronic structure in twisted Bilayer. So in my view, I would like to classify all the experimental facts into two categories. One category shows the locality of the correlation, like the STM at a higher temperature above TC. The spectrum here looks quite similar to that of a quantum dot. So it reveals that the correlation is very local. But some other reviews delocalize the electronic states, like the superconductivity and the topological states. So I think the simplest phenomenological model to describe this system is a heavy fermion-like model, which consists of some local degree of freedom and some delocalized degree of freedom. But we didn't actually, this sounds very natural, but we did not construct this model from this logic. We constructed this model by the topological quantum chemistry I explained yesterday. So basically, we can figure out the full symmetry group of this system. It's a magnetic space group for each valley. And after we know the symmetry group, we can label all the levels in the band structure by the representation of the group. All these labels are just some representations. I do not need to explain their actual meaning. And also, as I explained yesterday, it's possible to tabulate all the possible EBR, all the possible local orbitals in real space. And so if we do not do this comparison, if we do not try to decompose this into EBRs, what model we would like to write down for this two-band system? So first, it's a triangular lattice or hexagonal lattice. Second, it has two bands. So the most natural guess is that it's a honeycomb lattice, right? Honeycomb lattice has the correct symmetry and has the correct number of orbitals, but it turns out not true. So now let's compare this IRAPS to that of these EBRs. So this 1A position is basically the triangular site. And we see that none of these columns match these two orbitals. For example, this PXPY at the triangular lattice matches at the M point, also match at K point, but does not match at the gamma point. And we can also look at the honeycomb lattice. 2C is the honeycomb lattice. And if we put a single orbital, it could be S or PZ on this honeycomb lattice. And we can see neither of them match these two flat bands. So this comparison tells us that it's impossible to write down a two-band lattice model that correctly reproduce the symmetry character of these two bands. Later, it is found that the underlying reason is that these two bands has a so-called fragile topology. Okay, but there are some very beautiful work on the two-band models. In all these works, some symmetry must be broken, like C2T symmetry or the valley symmetry must be broken to write down a two-band lattice model. So this is something about the particle hole symmetry. I don't think it's very relevant here, so I just skip this. And as I mentioned at the beginning, some experiments see some quantum dot-like behavior. So that means there must exist some local degree of freedom. So we need to figure it out. And it seems contradicts with the fact that these two bands cannot be written down as a two-band lattice model, right? But we find that even though these two bands cannot be linearized. It's very close to a local orbital in real space. Let's compare these two bands with the px-qy orbital on triangular lattice again. We find that they match at the key point and they match at the end point. The only momenta where they mismatch, it is a gamma point. In this local orbital, we have gamma 3, but in these two flat bands, we have gamma 1 and gamma 2. But fortunately, gamma 3 is not too far from the flat bands, right? So I give it a try. I construct some Gaussian type px and py orbitals and calculated the overlap between these local orbitals and the flat bands. The red dots is just the initial try, my initial try. So my initial try is very good in matching this flat band. So when I obtain this, I'm super happy. And after we obtain this overlap, we can feed these overlaps into the machinery of Wannier 90. It's a standard tool to obtain maximum localized Wannier functions. And after this optimization, we found that basically 96% of the flat bands could be contributed by the localized Wannier functions. But there are 4% cannot be written down on these Wannier functions. Actually, this 4% is essential for this problem because otherwise the system will be really a quantum dot system. And to obtain the model for the remaining degree of freedom, we construct this projector PF onto the Wannier functions. Because we construct the Wannier functions numerically, so we can explicitly write down the projectors. And we define the projector into the remaining space as PC. And we can diagonalize this projected BM model projected onto the remaining space. And the blue line is just the band structure of this projected Hamiltonian. It has a quadratic touching point at 0 energy and 2 dispersive bands. The gap is not too large. It's just 20 or 30 MeV. So if you are familiar with graphene, you may immediately recognize that this is nothing but just the band structure of AB stacking graphene. So, and we can also write down the effective model analytically. Basically, this is simply constrained by the symmetries. And all the parameters we can read from our construction. So now we have a simple picture for the band structure. So so I have explained that the Wannier functions are located at the triangular lattice, which is the AA stacking regions. So at each AA stacking region, we have, in each per valley per spin, we have 2 localized Wannier functions. We term them as the F electron, and they are very localized. And at the AB stacking regions, there are the delocalized Dirac fermions. And the full system should be realized by coupling these 2 different kinds of carriers. Actually, this was also realized before our work. For example, in work by Zhida in 2019, they expand the Maury potential around the A stacking region, and they found that the Maury potential has the form of a pseudomagnetic field, and which is very strong. And they solved that problem and found there must be a localized 0 Landau level at the AA region. Later, we realized that our Wannier function pictorially is identical to their 0 Landau level. Okay, so now let's see whether this model works. So on the left-hand side, we have it's the delocalized limit. The blue bands are the Dirac fermion from the AB stacking regions, and the red line is the localized states. They are decoupled from each other. And now we continuously turn on the coupling. At the 0 energy, there are 2 gamma 3 representations, and the coupling will push one of them to the higher energy and push the other to the lower energy. And at some point, these 2 gamma 3 will cross with gamma 1 and gamma 2. After the band crossing, gamma 1 and gamma 2 are remained in the flat bands, and the topological flat bands are formed. So we can understand this process as a band inversion process. In these plots, the black lines are from our effective model, and the red dots are from the original BM model. We can see that they match each other very well within the energy window of 70 MeV. Okay, so our model works very well for the single particle part. And the next thing is that we need to project the interaction onto this model. So the advantage of this model is that basically only the f orbital is strongly correlated, and it forms. What's the question?
So yeah, the band structure matches. Have you compared the Bayer curvature distribution as well? How do they match?
They also match very well. We explicitly calculated this. It's in the appendix of the paper. Yeah.
I see. Yeah, thanks.
So basically, we construct this model initially, like around 1 year native to a DFT calculation, because all the bases are constructed numerically from the original model. Yeah. Okay, so the advantage of this model is that we can analyze the correlation effect on the very localized f orbitals. So when we write down the interaction Hamiltonian, we find that the most important interaction is the on-site Hubbard U of the f orbital. It's U1, and U1 is 60 MeV. It's much larger than the bandwidth, and actually this is the largest energy scale in this problem. And this G is some kind of ferromagnetic coupling between F and C electrons, and there are also some other density interactions. They are not very relevant to the following discussions. Okay, so before I talk about the pairing mechanism, I have to quickly summarize the correlation physics we obtain from this model. Okay.
Just a question on the delocalized electrons.
Mm-hmm.
So, it's like AB graphene,
yeah.
right?
Yeah.
So if there's a slight displacement field or some remaining space,
yeah.
This might open up a gap.
Right. So yeah, this is a very interesting question. So basically we have AB region and the BA region, right? So if this is AB, then this is BA, right? And if you apply a displacement field in the Z direction, both this region and this region will become gapped. But in the middle, there will be a domain wall, and there will be some helical states on this domain wall. So equivalently, you can write this model as F electrons coupled to a set of helical wires. And basically, the band structure looks the same. Yeah. Okay. And so let me quickly explain what we obtain for the correlated physics. We run DMFT plus NRG calculation for this system, and here is the spectral function we obtained. It mimics the STM spectrum. The horizontal axis is the bias voltage, and the vertical axis is the gate or the doping. So we can see that as we dope this system, some Hubbard band fall down from high energy to the zero energy, and at each integer filling, in the metallic region, in the fractional fillings, there are some zero energy peak pinned around the zero energy, and we interpret this as some kind of Kondo resonance. And at the integer fillings, we see that the width of this zero energy peak becomes almost zero. That means the correlated insulator must win at the integer fillings. We can compare the energy scale of the obtained Kondo temperature and RKKY, and we can see that the RKKY always win at the integer fillings. Actually, at that time, when we did this calculation, we have not included the electron photon coupling. And it turns out that all these Kondo temperatures are overestimated. And now we are running calculations with electron photon couplings. When the electron photon coupling is included, we find that the peak between 1 and 2 are still there, but the peak between 2 and 3 may disappear because the electron photon coupling will strongly suppress the Kondo physics. I will explain this later. And we can also compare this to the experimental spectrum. For example, in this experiment, we can see that between the filling 1 and 2, there is a zero energy peak like thing around here, right? And if you increase the temperature, it disappears. So we interpret this as the Kondo physics. Okay. So I think I don't have much time to explain the many details for this calculation, so I just skip this. Okay, so basically those calculations just provide a background for the pairing mechanism. Then let's go to the pairing mechanism. So as I explained at the beginning, we expect that the pairing mechanism here is very similar to that in fluorides. And we mainly focus on the filling between 2 and 3, where the superconductor Tc is the highest. And according to our previous calculation, we believe that the parent state of this superconductor is a Fermi liquid. You may also term it as a heavy Fermi liquid, but I think that's not very important. The terminology is not very important. The crucial thing is that we believe the crucial assumption here is that we assume the parent state of the superconductor is a Fermi liquid. And to describe this Fermi liquid, we also assume the locality of correlation. So in a DMFT spirit. So now let's write down an effective model to describe a local Fermi liquid around AA stacking region. So it's like a fluoride cage. So for now, we just focus on a single cage or a single unit cell. So this is the free part of the action. It has 2 parameters, the Fermi energy and the hybridization. And as I will show later, these quantities will not enter the conclusions of our analysis. They are, in the end, we will, all the physical observables will only depend on the Kondo temperature. So now let's just assume there is some Fermi level and there is some hybridization function which describes the hopping between this site and the bus around it. And the dominating interaction term is the Hubbard U. And this U is like 60 MeV, so it's dominating. And if we add these 2 terms up and we solve this single-sided problem, it's a standard Kondo problem. So we will obtain a Fermi liquid characterized by a Kondo temperature. But this cannot. I don't think this can explain the superconductivity. We must include some other interactions. So the first interaction, the first additional interaction we include is the electron-phonon coupling with the K phonon in twisted bilayer graphene. This mode is also discussed in this paper by Wu Fengcheng and McDonald, and they found that this electron-phonon coupling may favor a D-wave pairing channel. And recently, this phonon is also observed in RPAS experiments, which may tell us that the electron-phonon coupling between this K phonon and the electronic states is indeed strong, even though its relation with superconductivity is unclear. But I think at least we know the coupling is strong. And also, this electron-phonon coupling is also studied in this work by Fabricio in 2019. And this coupling is termed as the Valley-Young-Taylor effect. It's a very interesting name, which may suggest some physics like fluorides. Okay, and there are some mean field calculations for this mode. And I just said something wrong. The ground state favored by this electron-phonon coupling is S-wave pairing, but the second lowest energy state is a D-wave pairing. Okay, so anyway, we think this interaction is important. So we include it in our model and write down it on our heavy Fermi basis. And this is the resulted Hamiltonian. We write it as GA. We can see that it favors the singulates between 2 values. Here, eta is the valley index. So eta bar is the other valley. And this is the anti-ferromagnetic coupling. So we term this GA as the anti-Hans coupling because it favors small spin state. And we can estimate that this GA is of the order of 1 to 3 MeV, I think. Okay, so that's the first additional interaction we considered. The second interaction we considered is the Hubbard U on each carbon atom. So basically this habit U is will introduce a Hunt's coupling on the effective f orbitals, which favors the large spin, states, but it's a Hunt's coupling between different orbitals. So it acts in different channels with the anti-Hunt coupling. So these two terms do not simply add together; they act in different channels. And so the global ground state will be likely in the channel of inter-valley singulate, and how to say this? They tend to form singulate between two valleys, but triplet in the same orbital. So yeah, but anyway, it's just some parameter in the Hamiltonian, and we can treat this anti-Hunt coupling and this Hunt coupling as free parameters of the problem, and we can diagonalize the two-body problem and find the two-body ground state. We can see that in a large region of the phase diagram, the two-body ground state is D wave. It forms the E2 representation of the symmetry group. Basically, GA favors A1 favors the S channel more, but GH disfavors this S wave. So with the intermediate GH, the D wave becomes the ground state. But I would like to emphasize that this phase diagram is not a phase diagram for the superconductivity, because we do not include the Hubbard U yet. If we include the Hubbard U, all the two-particle excitation energies are positive. So this energy, they are given by this energy and this energy for the D wave and S wave. U is dominating, so the two-particle excitation energy is always positive. That means pairing is not favored in this system. So the problem is U have to resolve. So our work is try to resolve the problem of this dominating U. Okay, so now let's go back to the effective model, and we find that if we assume the Kondo temperature, first we assume the parent state is a local Fermi liquid characterized by a Kondo temperature. Now let's consider the limit where the Kondo temperature is much lower than the GA or GH. We find this limit, in some sense, could be solved. So to simplify the problem, yeah, even though this is already a very seemingly very artificial limit, it's still very difficult to solve. We cannot do it, so we needed to further simplify the problem. And we argue that when Kondo temperature is much lower than the multiplet splitting, which is GA and GH, when the local Fermi liquid is formed, only the ground state manifold will participate in the local Fermi liquid. I mean, only these two ground states will participate in the Kondo physics. So if this is true, we can do something to the excited state without changing the low energy physics. The thing we did is that we make all the excited two-body states degenerate. So we assume the ground state, the two-body ground states has energy U minus 2G, and all the other states has U. So the advantage we can take from this simplification is that the symmetry is enhanced, and we can make use of symmetries. And I would like to emphasize that in the simplified Hamiltonian, the interaction is still positive definite. So the two-particle energy is still positive. So I would not expect a pairing in a naive mean field theory, right? So, but we know that this is a strongly correlated Fermi liquid. So all the parameters can be strongly renormalized. And our job is to find the renormalized parameters, which cannot be obtained perturbatively. So we must use some non-perturbative method. So basically, our job is to calculate this full vertex function. It contains all the possible Feynman diagrams, and no one knows how to compute this exactly, right? And but fortunately, we can make use of the symmetry to determine the exact value of the renormalized interaction. So the mathematical tool we will make use of is a so-called word identity. Basically, basically you can consider to make a gauge transformation for your Fermi field, and this gauge transformation will change your Green's function. And because it's a gauge transformation, you can easily calculate it. You can easily calculate the change in Green's function. And on the other hand, you can also write this gauge transformation as a perturbation to your system, and you can apply linear response to your system and obtain an expression for the change of this Green's function. And because we are calculating the same thing in two different ways, they must equal each other. And after some derivations, we can obtain this very useful result. Let me explain this result. So on the left-hand side is the susceptibility of the bare particles. So O could be the electric charge, could be spin or angular momentum. So this chi-O is physical observable. And on the right-hand side, all the parameters are the renormalized parameters for the Fermi liquid. So the bare values do not enter this expression. So all the parameters on the right-hand side is renormalized. For example, this delta 0 tilde is a renormalized, is the Kondo temperature, or the critical, or the energy scale of the Fermi liquid. And this gamma tilde is given by z squared times gamma. Gamma is the full vertex function, and z is the quasi-particle weight. 10 minutes?
10 plus the questions.
Okay. Oh, so maybe I should go fast. So anyway, the good thing is that this equation establishes an exact relation between physical observables and effective renormalized parameters. And the way we can make use of this equation is that even though we do not know how to calculate the quantities on the right-hand side, we know some asymptotic behavior of chi-O on the left-hand side. For example, in this system, we have assumed that TK is much lower than the multiplet splitting. So many degrees of freedoms are frozen. For example, the charge is frozen. That means chi C must be, it's not 0, but it's very small. It should be much smaller than the inverse of the energy scale of the Fermi liquid, because Fermi liquid is not contributing to this charge fluctuation. So we have a set of constraints, and this set of constraints help us to determine the renormalized parameters. And we find that the renormalized U1 become negative. And we can prove that at least one of the parent channels now have negative eigenvalues. So basically, under the approximation we adopt, we prove that even though the bare interaction is positive definite, the renormalized parameters become attractive. And you may doubt whether our method is valid for this system. The good thing is that it's not invented by us. It's invented by some experts in the field of Kondo physics. So if we apply this method to the standard Kondo problem, we can reproduce the base ansatz result. So this framework is very reliable, as long as we take the assumptions we made at the beginning. Okay, so basically we proved the existence of a pairing channel in the limit where TK approaches 0. And we can also analyze the other limit where TK is much larger than the multi-split splitting. And we find that in this limit, when U is much larger, the pairing channel vanishes. So the pairing channel only exists for an intermediate strength of TK or of U. Okay, so in this part I explained how a pairing channel emerges in this problem. And then we can, after we obtain this pairing channel, we can apply a mean field theory to the system using the renormalized parameters. This is the phase diagram we obtained. So now we treat the renormalized interaction, which is negative, as a tuning parameter. And we find that in an intermediate pairing strength, the ground state has a nodal pairing structure. And even though the underlying pairing symmetry is D wave, but here on Fermi surface, the nodal structure looks like P wave. This is because we use the renormalized quasi-particle spectrum. And in this renormalized quasi-particle spectrum, there is a pair barrier phase on the Fermi surface, and we can prove analytically that this pair barrier phase will enforce 2 Dirac nodes on each of the Fermi surface. And if we continue to increase the pairing strength, then these nodes on the 2 Fermi surfaces will merge each other and open a full gap. So this nematic phase could be either a P-wave-like gapless superconductor or has a full gap. And if we calculate the density of states in the 2 states, we can see that at an energy scale much larger than the gap, which is 0 in this case and finite in this case, the density of states will look like V-shaped, right? So I think this matches some observations from the experiment. And also, this theory is inherently BEC-like. Let's consider the energy scale again. So the Fermi energy is at the same scale of the control temperature, or the energy scale of the Fermi liquid. And the renormalized interaction, according to our calculation, is like 4 times TK. So that means the pairing energy is larger than the kinetic energy. That makes the pairing in the BC limit rather than the BCS limit. I think this is also consistent with some observations where the pairing gap is much larger than the critical temperature. And this experiment, as I mentioned at the beginning, seems also consistent with the fact that the coherence length is very small. In real space, the pairing is like a molecular pairing. It's formed by the Kondo cloud around a single unit cell, so it's quite localized in real space. And before ending my talk, I would also like to present some ongoing calculations. All these analyses are analytically, and we make some assumptions to enable this analysis, but we also want to do some solid numerical calculations. And this is still ongoing, so let me present some result. For example, we calculate the DMFT spectrum at several fillings. So here I only present the result at the integer filling -2. So this is a measured STM spectrum. There are 2 peaks around the gap, right? And this feature continues as you dope the system. So at a small doping, you still have these 2 peaks. I think this is also presented in the last talk. And on the right-hand side are the calculated spectrum. For example, we can look at the yellow line here. And the different colors means the different strengths of electron phonon couplings. We can see that this yellow line resembles very well with the measured spectrum. And I think this also gave us an explanation for this gap structure. As mentioned in the last talk, before we enter the superconductor phase, we already have some gap-like feature in the metallic phase, right? So one may ask, what's the nature of this gap structure? And from our calculation, we see that this gap are contributed by the multiplet splitting given by the electron phonon coupling. So basically, we can treat each AA site as a superatom. And when electron phonon coupling is considered, the many-body states in this atom split. And when you measure the single particle spectrum, those multiplet splittings will enter your measurement. And we find that this gap is exactly given by the splitting between the 2 particle ground states to the first 2 particle excited states. So I think, yeah, so maybe this feature in experiment could be explained using the electron phonon induced multiplet splitting. Okay, so this is, okay, I think I can stop here. Oh, so I need to acknowledge my collaborators. All these analyses are done by my students Wang Yijie and Zhou Gengdong, and I also need to acknowledge the collaborators Lian Biao from Princeton University, Tong Ninghua from Renmin University, and Peng Shui from Caltech. And we are also doing numerical DMFG calculations with Seong-Sap Lee from Seoul National University. And I also would like to acknowledge my previous advisors, Bernavig and Zhida, because we proposed the model together with Bernavig, and Zhida taught me a lot of physics in the fluorides. Yeah, okay.
I believe you also did some symmetry analysis of this basis for the order parameter, right?
Yeah.
So, like, what group did you use for this, like, as a normal
state? We assume the C6 symmetry. So the point group here is D6. Mm-hmm. So in practice, the active symmetry might be lower than this. Yeah.
Okay, thank you.
Mm-hmm.
I have a question.
Mm-hmm.
On your cascade diagram, can you go to that?
Yeah.
If I remember correctly, this is in logarithmic scale, the cover scale. See?
Sorry, you mean this?
Yeah. So you don't seem to have almost any spectral weight when close to the charge neutrality. You only have spectral weight in the positive band, and you don't seem to have any spectral weight.
Yeah.
You understand that?
Yeah. So first, I think this also matches the
it's different to ours, and also I think to
I see. Sorry. Okay.
So
yeah.
Like
okay. So in this calculation, we have zero spectral weight at zero energy because we are using NRG, and NRG cannot run for the 8-flavor model. So at the first step, we simplify the system to a 4-flavor problem. And for that 4-flavor problem...
Okay, but then you are breaking the symmetry. And
so So this is with a broken symmetry assumed.
Yeah. You're assuming that you have all the Bilayer symmetry broken.
Yeah. Otherwise, we could not run this NRG calculation. Yeah. It's too heavy for NRG. Yeah, but I think in other calculations, even though there are some spectral weight at the zero energy, it's very small, I think.
No, but it's it's not, I'm not saying just that the charge neutrality is that somehow it's very different in terms of the so somehow the features of the Hubbard band.
Sorry, I don't understand your question. You mean this?
Yeah.
You mean Yeah, sure. Yeah, sure. Basically, in our model, we omit those part of degree of freedom. Otherwise, we cannot run this energy calculation. Yeah, there should be one. Yeah. Okay. Mm-hmm. Okay. Mm-hmm.
More questions?
Okay, thanks.